Yeah. For everyone watching this in the recording, a very warm welcome to the second episode of Revolutionize STEM's webinar series. Today we have Nefeli Moridis, if I'm pronouncing that correctly, and she is a developer relationship manager who will be going through the process of obtaining a PhD and being a researcher and with her background in petroleum engineering, she will be giving us first-hand experience of how it is to be a woman in STEM. So thank you for doing this, Nefeli.
Thank you for having me. Will you please enable the share screen option for me?
Yeah.
So I can share my screen with you.
I have enabled it.
We probably need to stop the recording. I need to restart my Zoom to enable the shared video.
Okay, so do you want me to stop the recording? Can you hear me? Hi, can you hear me? Hi, can you hear me now?
Yes, I can hear you. I cannot see you.
All right, just 1 second. Yeah, you can go ahead.
Okay. Great. Well, thank you all very much for having me today. I will share my screen with you. Can you see my screen?
Yes, it's visible.
Great. Well, thank you all very much for having me today on this Revolutionize STEM webinar. My name is Nefeli Moridis. I have a PhD in petroleum engineering. And today's talk, I will go over the path to PhD and talk a little bit about my research and then my experience as a woman in STEM. If you have any questions at some point, submit them and then somehow I will get back to you and answer them for you. So my family is from Greece. That's a picture of me in Greece one summer when I was home. And I had the opportunity growing up to go back to Greece every year and see my family because I actually grew up in California. So every summer I would travel back home to Greece and see all of my family that lives there, my extended family. My parents and my siblings were the only ones that lived in the US. But when I was in high school, what I had the opportunity to do was the International Baccalaureate. And with that program, you have options to take higher level courses. I believe that 2 or 3 are required. I ended up taking a higher level chemistry, a higher level physics course, and then I also took higher level English and French classes. So I always knew that I wanted to do something within STEM. I didn't know when I was in high school what that looked like, but I was interested in math. I was interested in chemistry. I was interested in physics. And so, having those opportunities in high school really started getting me thinking about what I wanted to do. So a bit later and through high school, when it came time to be applying for different colleges, different universities, I applied only to engineering programs. And I applied to engineering through California. I applied to schools in Texas, and then I also applied to schools on the East Coast. And what I ended up doing was attending the University of Texas at Austin. And I joined their petroleum engineering department. So I moved to Austin when I was 17 after I finished high school. And I started my, work within the STEM field with my undergraduate degree. The first 2 years at UT, and I believe in most universities in the US, really focus on completing all the prerequisite courses for any engineering degree. So we focus on, the physics, the chemistry, the advanced math courses like differential equations. We had statics courses. We had like intro to petroleum engineering courses. We also had to finish some requirements for humanities courses. So with that, I took French, and because of my higher level work with my international baccalaureate, I was able to do a minor in French with only taking very few courses. So those were really the first 2 years of what that experience looked like. In the petroleum engineering department, they were really, really stressing the importance of having real life experience. So with that, I was able to start doing some internships over the summers. The first summer I was in college, I worked for the Berkeley National Lab, Lawrence Berkeley National Lab in Berkeley, California. And I did research on hydrate methane and how it's produced in different properties. That was a shorter internship, but that was really more research based. And then the next few summers, I worked for a company called Total. Total is one of the major oil and gas companies. This is me on a platform in the Gulf of Mexico. So with Total, I was able to have different opportunities, working and getting like real life experience, working Gulf of Mexico projects. And I also did work on an unconventional reservoir project. The reservoir is called the Barnett Shale. It's located in Dallas, Texas. And so really got a lot of different experience being in applying what I learned in school in real world applications, and having that opportunity was really exciting. And I focused only in the reservoir engineering side of the oil and gas industry. The oil and gas industry is really split up into 4 sections. One is drilling, another one is reservoir, you have production, and then a lot of the geoscience background that goes into it. So really those are the main factors when you're thinking about petroleum engineering. So this was very exciting. I really liked working on the platform. It was really cool to see, what you could do in the real world. And I think this was the second summer I was working with Total. Because I enjoyed what I was doing so much within my internships and then with what I was learning at school, I decided that I would start thinking about going to grad school. And so before graduating from UT, I decided to apply to this dual master program that Texas A&M University has with IFP school, which is a school in France. So after I graduated from UT Austin, I moved to Paris to start my adventures within grad school and, the next chapter, which was really fun to be living in Paris for the first time. When I was there, I graduated with my master's degree in reservoir geoscience and engineering. This was again focused specifically on reservoir applications. And IFP as like a learning environment is really different than any other university in the US, for example, in terms of that it's really project-based. Courses are all day from 9 a.m. to 4 p.m. Whereas my experience at UT was that you have certain courses during the day, then you have free time to do studying, homework, etc. So a very different way of teaching, which I also really enjoyed. So when I came back after I finished at IFP, I started my master's in petroleum engineering at Texas A&M. This is a picture of me under the Aggie Ring, which is a big Aggie tradition that once you have completed enough coursework, you are eligible to get this ring. So that was me on my ring day celebration underneath the statue of the replica of the ring. A&M has many, many traditions. It's very exciting. You know, there's so many different things that they do. So this was all new to me as well. While I was doing my master's at A&M, I started teaching as a source of income and as well like experience. So I taught for 7 years total between my master's and my PhD. And that really, really was a great path for me. I enjoyed teaching. I enjoyed having discussions with students. I enjoyed the interaction with students. And additionally, what I didn't know would happen is that I would become more and more comfortable speaking in public, right? So that helps with, for example, presenting papers, which is that next picture that you see. So on top of the research that you do within any master's program and the subsequently PhD programs, you're able to publish your work. So that you can present to the STEM community that you're a part of, the work you've been doing, why it's relevant. So having a paper accepted is a very exciting, thing, but it's also a very big deal within your, academic career in grad school. So this was me presenting at my first conference. This paper was based on my master's research, and I presented this paper in Buenos Aires in Argentina. I've also published 10 other papers since then. This is just a little snip of their titles, and it's not a in-depth picture, but what's really exciting, apart from being able to do all these presentations and like having your work published and then people can read it and discuss it, is that you also get to travel for these conferences. So I've been able to present in conferences in Australia, California, in Denver, in London. You really get all these exciting, additions to not just presenting, but all the extras. And so, because I really enjoyed that first portion of it for my master's, I decided to continue on to do my PhD. And I started my PhD in August of 2015. When you start your PhD, there are different steps that are involved within the process. And I believe that they differ for every school, but the main gist is that you come in, you have to take what we called in our department a qualifying exam. This was a set of 4 exams and an essay, and you had 2 shots to do it. And after you passed all of that, you were technically considered a PhD candidate, but until then you were just a student. And once you become a PhD candidate, you continue with your coursework. I continue teaching, research, etc. But then your next step is your preliminary exam, which is basically your defense of just your research topic and what you think you want to present to your committee and what you want to work on for the next few years. So in that stage of things, people on your committee can say, no, I don't think you're ready, or you need to include more work, or you probably need to remove some work. But overall, it's the next step. And once you pass that, then you're really in the last stretch of doing your research. You've probably completed all your courses by that point, so you can really focus on your research. And again, I was teaching, so I was doing the both. So I was able to successfully defend my PhD. That's me with my committee. So my committee was made up of my 2 advisors, this man here in red, and this man here in the overalls, and then 2 other professors, one from a different department and one from the same department. And so they, after I presented all of my work, questioned me for about an hour and a half, and then I had to answer those questions successfully. And after that, they told me that I had passed. So that happened in March 2020, so a little over a year ago. So that was really my path to PhD. I thought I would go a little bit into petroleum engineering, since this is my background and the work that I've done in the field that I've been in. So I find this cartoon very funny. I know it's not technically correct, but the black here with the dinosaur represents oil, and then this here represents gas. So you produce oil and gas. And though not technically correct, all oil and gas is made up of organic material. So we can just take it as an intro joke. But this is a more, a better understanding of what it actually looks like in the subsurface. So this is what we would call a conventional reservoir. It's conventional because you see this reservoir rock is really like regular rock that has like space between the grains. And so within those grains, you have gas that sits in there, you have oil that sits in there, and then you have water that sits in there. So if you look at this image, this graphical representation, you have your free gas on top, then you have your oil, and then you have your water. And the reason they're layered like this is due to densities, right? So you have this cap rock on top here, which is a seal, and the seal makes sure that the hydrocarbon stays there. Without this seal, your gas and your water and your oil would start migrating in different directions and you wouldn't have a reservoir, it would just be dispersed. So this really is to contain your hydrocarbon where they live. So the big question that we try to figure out in petroleum engineering is how can we determine how much oil and gas there is, right? We need to be able to do this in a way that is economical. We need to make sure that there's oil and gas there to produce, because if you think about it, these different wells here that are shown are very expensive to drill and to maintain. So you want to be sure that your project will be successful. So this leads me to my research. I know there's a lot happening right now on this slide, so just I'm going to walk everyone through it, but there are different types of reservoirs. This cartoon was just one example of a very simplistic conventional reservoir, but we have reservoirs that are called unconventional reservoirs. And the reason that they are called unconventional is because compared to the rock I just showed you that has space between the grains, so oil and gas can like fit there and they can move through. These don't have any space because they're made of clays. So these pores like lay one on top of the other like this. And so there's very little space for the oil and gas to be there and move around. So these reservoirs are really what's being produced right now, specifically in the US and in certain other countries. Like Argentina has a really big unconventional reservoir called the Vaca Muerta Shale. The biggest one in the US is the Permian Basin that's located in West Texas. There are several in Texas that go through Mexico. There's one on the East Coast. Basically, they're everywhere. And they are being developed because they hold a lot of oil and gas still. However, because these rocks are so different from the conventional reservoirs, they're a lot more challenging to produce. So you need to, instead of those wells that I just showed you on the cartoon that were straight down into the formation, these ones are horizontal. So they go like this to be able to access as much as the reservoir as possible. But additionally, because there's not any room, because all of the layers are like on top like this, there's no way for oil and gas to move into the well and then be produced to the surface. So what you have to do is create what's called a hydraulic fracture, which is a lot of water being sent into these well bores and creating these big like cracks. And then that's how the oil and gas gets to your wellbore. So it comes out of the reservoir into this high permeability. Permeability is the flow, the ability to flow between grains. So this high area where there's a lot of space for the oil and gas to go, and that's how it's produced and then goes to the surface. So with all of that, what's challenging here is that the equations that we have don't really work for these reservoirs because they assume that there's space between the rock to make these calculations. And so now that there's no space between the rock, the equations are no longer viable. So how do we solve that problem? That was a really big portion of my research. And the answer is that you do a combination of engineering, of statistics, and probability. So you take the equations that you already have, and instead of just using one number for each parameter, you build a distribution of values on each parameter, and then you get a distribution of results. So for example, if you put in let's say 3 different values, just like 3 specific values for one of the parameters, then you would get 3 specific results. However, if you implement like a Markov chain Monte Carlo, which creates this full distribution of values, then you get a full distribution. So then you have a probabilistic result at the end where you can have like a P90, which is a value that is your lowest estimate. And then you have values like P50, you have P10, and basically this just gives you a range. So you can go back and say, well, I'm not sure that this one number, but this is the probability that the amount we can recover falls between these 2 values or these 3 values. So that's a lot of the work that's being done and a lot of the work that I focused on while I was doing my PhD. So why does all this matter, right? We discussed, how to do these different estimates and why they're important. But the reason they matter is because apart from your company needing to know how much they can produce and like what they expect with the economics, every publicly traded company in the US needs to present these volumes to the government. In the US, it's called the Securities and Exchange Commission, SEC, but I have done consulting for companies abroad that also focused in the same thing, and they don't have to go to the SEC, but they go to whatever governing state, place they have within their own company. So if your volumes are very incorrect, then you are audited, and there are a lot of fines associated with that. So that's very, it's not great. You want to avoid that. So this table here on the right basically shows what the guidelines are for your volumes. So when you're reporting, you only report this 1P. This 1P is just like your lowest estimate. And like I previously mentioned, if you're doing a probabilistic analysis, this would be a 90%, right? And these are called your proved reserves. And reserves are just the volume of hydrocarbon that you have that you're producing right now. So when you put all of your projects together for your company, you have this, value, this 1P value that you can report, excuse me. So when you look at the 3 of them though, like I discussed earlier about your probabilistic ranges, these results are, this is your P90, your low estimate probabilistically. This is your P50, your 2P, which is your best estimate. So if you had to make a best guess without doing any probabilistic or statistical analysis in your work, that would be your 2P. So like whatever you think is probably the best. And finally, like if you're really optimistic, is your 3P. So your very high guess, or not guess, but your very high estimate is what your 3P is. So these really help your company understand and track all of the hydrocarbons that you have for your different projects. Because of the difficulties of forecasting for these unconventional reservoirs, like I mentioned, a second big portion of the research I did was building mathematical relationships between these 1P, 2P, and 3P volumes. And we did that because we implemented a probabilistic approach initially. We were able to create a mathematical equation to relate these 3 volumes. I'm not going to discuss the contingent and prospective resources here. I really wanted to focus specifically on reserves because they really are what you're producing, what you're selling, and what a big portion of the oil and gas that we're dealing with is. So this work really was to help a lot of companies with their understanding of how to accurately get these numbers and then how to accurately relate them together. So as you can see, there are so many challenges here that we're facing, right? And I think the biggest and most exciting is that you as a petroleum engineer or as a geoscientist working specifically in oil and gas, you never look at what you're working on, right? Like if you are in aerospace engineering, you can see what you're working on, you can see the rocket, you can see different parts, etc. But when you're working with the subsurface, you can't go down and see what your reservoir looks like. You can't really, look at it. So all the work that we're doing, we have different tools for imaging, and we have different tools to understand like what the formations look like, but we can't actually go down and see it, right? We have to interpret all of these images that we obtain. So that is, the biggest challenge, but also the most exciting part of this process. So to summarize all of this, I know there was a lot of information that was discussed, and I'm happy to go into more detail if you would like, but to summarize, I used these combinations of methods to provide these probabilistic ranges, and from there was able to build a mathematical function to relate those volumes. And this, again, was really important so that different companies can better understand how to get these volumes, then how to relate those volumes for their internal needs and tracking purposes. I did similar work for a few companies that I did consulting for while I was doing my PhD, and those are projects that I worked on with my advisor. But the science is the same regardless of where you are, right? You have challenges in conventional reservoirs, but your estimation methods are very similar. You have challenges in unconventional reservoirs, and again, you have the same challenges as you would in the US. So as far as like reservoir to reservoir goes, there are of course differences in the geology of them and the depth and the pressures associated, et cetera, but there are certain similarities that we can place on each. All right, so the last portion of what I was going to talk to today is my experience as a woman in STEM. I just want to start by saying that these are numbers that are relevant only to my experience. This is not for everyone in STEM. This is not for every university. It's not for every position. It's not for every company, right? But I just wanted to start by saying that this was just my experience and how it's gone so far. So in my undergrad at UT Austin, I think we were about 50-50 women to men, which was great, very open. A lot of people after the first year dropped out, but I think dropped out not as left university, but changed departments. But this was pretty evenly split. When I started doing my master's program, there were more men than there were women. And then specifically as I moved up doing my PhD, I was the only woman in my cohort of 16 students. So there was, percentages get lower and lower as you move up. And that was just my experience of it. I've worked for several different companies. I've worked, along the way, but at my current company right now, I work for the global energy team, and there are 2 women, and our team is about 50 people. So this does not represent the whole company. There are several women that are in in leadership positions at my company. This is just how it ended up for the energy team within my company. And I wanted to briefly discuss the biggest lessons learned and what I would take away and what I would like to share along my way. The first one is to always advocate for yourself. I have been in positions where I thought that my supervisor would give me what I needed to do my job properly, and they didn't. And not until months later when I realized I didn't have the right information to base my work off of. So advocate for yourself. If you notice that something is incorrect, ask questions, stand up for yourself, speak up during meetings. If your supervisor cannot help you the way that you need to help, you can go talk to their manager. It's okay to ask for help always, right? So you need to be present for yourself, and you need to say, I think these are my opinions within work. I can back them up technically. This is the help that I need from you. And of course, there's a way to go about it very politely and very, professionally, but make sure that you are your best advocate. That's my number one. Along my second one is that you deserve to be there. So I've been sometimes told that I don't deserve to be there because of whatever reason, right? This is so untrue for all of you. You worked hard. You deserve to be where you are, right? If you're starting in university now, you have the grades and the background to be accepted into that program. If you're looking for internships and you landed one, you are the reason that you're there, not because someone was just being nice to you. Nobody will just give you a job to give you a job. You did all the hard work. You deserve to be there. So just remember that wherever you are in your life, don't let anyone tell you or let you believe that you don't deserve to be there, because you do. That's a big one. So remember your accomplishments. Remember that, you know, you being at that stage and having a success is because of your hard work. The last one is that you can totally do it, right? It's hard work. I'm not going to sit here and tell you that any of this is easy, or that, you know, you just show up and then, you know, it's just a walk in the park. No, you know, being in STEM, for everybody, you have exams, you have projects, you have homeworks, you have assignments, all of these things that take hours and hours and hours of your time. And you may see some of your friends in other departments that are having a little bit more fun than you because they don't have, you know, the workload that you have. I know it's hard, but 100% you can do it, right? If you're interested in doing it, if it's what you want to do, you totally can do it. And you will, at the end of it, you know, when you're done with school, you're going to look back and remember all the fun times that you had. You know, I have memories when I was an undergrad working until 3 a.m. with all of my friends because we were studying for exams, or, you know, working late to finish different projects that we were working on together. And those were some of my best times. So in the moment, it may seem like, you know, it's not so much fun, but I promise you, it will all pay off. And then, you know, for the big picture, with when you start your career, you don't get there just by not doing any of the work, right? So you will reap the benefits. If you want to do it, totally 100% can do it. And, you know, the exciting part of like starting your career, doing different internships, is that you get to see these real life projects, right? These real life problems and how you can help answer the questions and fix them and how to move things forward. So it is very exciting and it's very rewarding. And with that, I want to thank everyone for being here. I'm happy to answer any questions. Like I said before, I believe this is pre-recorded. So if you have questions, you can feel free to email me or reach out in any way. And I'm happy to discuss this further with any of you.
Thank you so much for doing this. I think you provided a very, very valuable insight to all of us who will be watching this. And I think your PPT was extremely well made with the graphics and bullet points that made it even easier for us to understand your explanation. And I think this is the perfect webinar for someone who is aspiring to be a petroleum engineer or being in any STEM field for that matter. Will really benefit after watching this. And thank you so much again for doing this. I will just ask you a few questions that we've gotten from people who had registered for the webinar.
Sure.
So the first one being, since it's May, the mental health month, and a major like petroleum engineering comes with a lot of pressure and a lot of obstacles. So what are a few things that you did that to keep your mental health in check as well?
That's a really good question, because for many years I didn't even consider it, and then realized the importance of that a little bit later on. But one big thing is to take time for yourself, right? If that means you need 1 hour to go on a walk or meditate or do yoga or take a bubble, whatever it is that you need to make sure that you're okay as well, because if you burn yourself out, you won't be able to continue, right? And these programs, any STEM program, is challenging and stressful. So definitely taking that time and recognizing that, you know, I need that time so that I can also perform my best, right? People beforehand, I was under the impression that you just work all the time, and that's how you become successful. But no, you have to take care of your health. So that's like cooking good meals for yourself. You have to take care of your mental state by, you know, taking the time you need to recharge and like relax, and then, you know, go and do your best when you're feeling great. So, yeah.
Right, that's really important. Thank you. And one question also being, since most of us are high schoolers right now, what would you suggest we do to pursue our interest in STEM field?
So if you're interested in doing it, I would recommend before moving into college or university to do your research, right? Figure out what do you want to focus in. You want to figure out what school is the best for what you want to focus in, and build a plan based off of that. So for example, when I was applying to colleges, I applied to chemical engineering departments and nuclear engineering departments and petroleum engineering. And all of those are energy related, right? Chemical engineering is used in the refining process, for example, after you have produced your hydrocarbon, it's refined. And then it's made into different products. So that's where chemical engineers will come into place. Nuclear engineering is another form of energy. So there are a lot of projects being done in the US. For example, one was called the Yucca Mountain Project. But you know, that was kind of where I thought I would land. So with that, I applied to universities that are very strong in engineering. So UT, Austin, and Texas A&M are both two of the best petroleum engineering programs in the country, in the US. IFP school in France is one of the best in Europe. So, you know, find the schools that you would like to go to based on your interest. I'm not well versed in like the medical field, for example, or how it works outside of the US beforehand, but, you know, find your school that you think you would thrive in, do your research. I don't know if there's an interview process outside of the US, but if there is, you know, make sure that you know why you want to do it. Right? If you're, say, going into medicine, telling them that you've wanted to be a doctor since you were 5, like it's not very impressive, right? You want to tell them what it is exactly about it that inspires you, what you want, what difference you want to make in the world. So that's really, I think, the best advice that I would give is to research it, look at what your interests are. And the good thing about college is that it's not the end, right? If you go through your undergraduate degree and you decide that you really hate what you just did for the last 4 years, you can either change while you're in school. I don't know how easy that system that is outside of the US, but in the US, you can change your degree pretty easily. And then you can also go to do a master's program. A master's program is usually 2 years, and you can be in a specialty that's adjacent to what you've done. For example, there are several mechanical engineering students that have a bachelor's in mechanical engineering that do a master's in petroleum engineering because they can be related. So you can do that as well.
Got it. Thank you so much. And lastly, the question is that, has there ever been a point where you or someone close to you has wanted to give up? And what has kept them motivated or kept you motivated to stay in the field?
That's a really good question. There are several times that I have not been motivated to continue because, again, it's hard, right? There have been times when I've wanted to quit. There have been times of, like, you know, semesters of very high stress, of sleepless nights because of the amount of coursework plus teaching plus, you know, research going on, that I've really thought that I couldn't keep going. But you have to take a step back and then think about why you're there. Why are you doing all of this? What is the big picture at the end of the day, right? So for me, I remember one semester, particularly when I was doing my PhD, I was taking an advanced statistics class, and I was also taking an industrial engineering course, all of these topics related to my research, which is why I wanted to take them. And I was also taking a petroleum course, and I was teaching, and I think the semester before I was about to present my preliminary exam. So I was very, very, very stressed. I was in my office until 3 a.m. regularly. I was working every weekend. You know, that semester was particularly difficult. And you just need to take a step back and think about it, about why you're there. You know, that semester was temporary, that time will pass, you know, and you'll be better for it at the end, because I needed those courses to help me with my research. And, you know, I needed to teach because that was my income, you know, through teaching with the university. So all of these things needed to be done for the bigger picture of being there. That being said, you know, it's not easy, right? There was still most of that semester that I was very miserable and exhausted, and you know, taking time for myself seemed like impossible because I was just working all the time and I was always stressed. So really, motivation is not like a day-to-day thing, right? You're not always motivated, but what you are always is committed. So you need to commit to yourself every day that you're there for the reason, right? And this doesn't necessarily only stick with your schoolwork or motivation, for example, but you just need to commit to what you're doing and then stick with it. And again, if you decide at the end of that this is just not for you, that's okay, right? You decide what you want to do with your future, with your career, with everything. Right? That there's no right course, there's no wrong course. It's just what you need to do. But yeah, my way to stay motivated is this bigger picture and like showing up for myself in the work every day, committing to doing the best I can do, even though going into it, I knew that the next day was going to be like just as hard. But also remembering that that is also a very temporary time in your life. So semesters of what, about 3.5 months? It's a hard 3.5 months, but you know, it's short-lived. So, you know, knowing that it will and knowing that it's like all for the bigger picture, and then just like, you know, showing up and doing it is really the only way to stay motivated. But again, I will say it's hard. You know, there are days that there are days that you're like, nope, I don't want to do this.
Right, right. Thank you so much. I think you gave us a very, very valuable insight, and all our questions were answered. And I think a lot of times people tend to think, like, even though everyone is ambitious, but there is a lot of hard work that goes into it as well. And as you said, there's you have to keep it a balance. Like few times, like some of the times you have to work and know that it's a um, short timeline. However, look at the big picture, and that'll keep you motivated. So I think you shared some very valuable lessons with us as well today. And thank you so much for doing this.
Thank you. It's been my pleasure. Again, for anyone in the audience, if you have more questions, I'm happy to answer them. If you submit them through Revolutionize STEM, I'm happy to go back and answer those at a later date. But yeah, thank you very much for having me. It's been a pleasure. I've really enjoyed it.
Thank you so much. Bye. Have a great day.
Thank you. You too.